So hello everyone. So welcome to our this week Rogers in Efficient AI seminar. And today we're very glad to have the Professor Pepe Zhou from the Brown University to give this talk, Efficient Programming on Heterogeneous Accelerators. And Professor Zhou is currently assistant professor at the School of Engineering, Brown University. And she received a PhD in computer science and a master in electrical and computer engineering from UCLA, and a bachelor degree from the Southeastern University. And her research investigates architecture, programming abstractions, and design automation tools for reconfigurable computing and heterogeneous computing. And he has published more than 40 papers in many IEEE ACM computer system and design automation conferences and journals. And especially her work has won the IEEE transaction on CAD Best Paper Award and some other prestigious award, including the IEEE ACM IGSC Best Viewpoint Papers and the IEEE SPAS Best Paper nomination and IC-CAD Best Paper nomination, so on. So now let's welcome Professor Zhou to give us this talk.
Great, thank you, Paul, for inviting me to this AI seminar. Efficient AI seminar has been very popular in our field, and thank you for the invitation, Professor Yuan. Thank you for the invitation. So as Professor Yuan just introduced, I graduated from UCLA after getting my computer science PhD degree. And then I worked in AI chip startup company for 2 years before I came back to academia, working as an assistant professor at the University of Pittsburgh for 3 years. And now, starting this September 1st, I work as an assistant professor at Brown. So my research focus can be summarized as from the low level to the high level, starting with this architecture, including different kind of chips, FPGA, AI ASIC, GPU and chiplet technology, and then how we program those chips, the programming abstraction and the compiler support, and all the way to the upper level, applications, and how we can use those chips for different applications, including artificial intelligence, genome, medical applications. And I'm fortunate to teach our undergraduate course and also graduate level course, including the reconfigurable computing, deep learning, computer organization, and also embedded system design. I'm going to teach a VLSI course next semester at Brown. So before I discuss all those heterogeneous computing or reconfigurable computing, why we need that in the first place? So this is one of my favorite slides, which shows these so the y-axis is the power dissipation in terms of watts per square centimeter, and the x-axis shows the different technology node. And you can see that this is by the way, this is a log scale. So you can imagine that the linear line here means exponential increase. So this power dissipation increases exponentially from generations to generations. And if we keep such kind of scaling trend, then we can basically cannot afford such kind of hot chips in our field. And this is how power dissipation, if we keep such kind of a scaling strength, it could be as the temperature can be high as the sun surface. So that's something that we cannot design. So that's exactly the reason why in the first place we introduced the parallelism. And the parallelism means that the multi-core or the multi-thread system, whereas we can scale out our performance without using that much heat. But this cannot give us the performance scaling without encountering this power or heating dissipation problem in the end. So that's the exact reason why we further introduced the customization, which is to adapt the architecture to the application domain so that we can still scale out our performance as the trend we expect, and then still while keeping this power consumption under control. So you might ask another question is that how we can achieve such kind of customization. And we have been doing this customized computing on using field programmable gate array FPGA for many years. given that FPGA can give us such kind of like energy efficiency as high as 10x to 100x, then these general purpose computing device like CPUs will what is FPGA and what does it look like? And can we program such kind of device in a very, let's say, in a short development time? And let's first look at this FPGA architecture. So this is a very high-level architecture overview about FPGA, where we have this arrays of logic element and arrays of this memory. And in the periphery of the circuit, we have this programmable I/O. So this key point is this lookup table, whereas we can change or configure the functionality of those lookup table by giving this different input, and then we have this output, but we can reconfigure the logic of this lookup table. And that's exactly the reason why we can change the functionality of those FPGA circuits even after we like fabricate those chips. And we can also reconfigure this interconnect. Well, here we show this lines and rows and columns so that we can change the connection among all those processing elements so that we can route our design or route our data from this source, but then at the next time we can route it to another like destination. And we have been successfully using this FPGA for this customized computing, or we call it domain-specific computing, domain-specific accelerators for various applications, including the genome, including this image and the video processing, or let's say the graph neural network applications. So this one is the stencil computation. So stencil is the one second. So stencil is one of the most used or popular kernels within this image or video processing. So here, this isn't an like overall architecture, but it shows that how we implement this FIFO buffer lines to maximize the data reuse within this kernel. And the second one, the lower part of this, shows how we implement this genome acceleration, which is this kernel is called a Bureau aligner, which is the one that given certain like in human genome inputs, then we can align those to the reference genome, to the position where this genome segments belong to. So that's the genome acceleration. So by using FPGA, we have been successfully accelerate those applications, shrink the runtime. To give you some sense or example, so for this genome acceleration, before our acceleration, it takes more than 49 hours, which is technically speaking, that's more than 2 days to process a single human genome on single core CPU machine. After our acceleration on using FPGA, then we can shrink this runtime by less than, let's say, 26 minutes. So we have like around like 50x speed up when using FPGA. So by using FPGA, we can that's where we said like we can do domain specific or application specific computing while we still keep our like design cost in a very reasonable time, because this doesn't require fab. It's not like a million budget thing, but still we can do this in a very good or reasonable like design cost, and also very fast time to silicon. That is a short development time. And we can do this for another application right away on the field. So that's the flexibility we can enjoy from FPGA. And there another example about using customized computing on FPGA is the Microsoft Catapult project, or Microsoft. This is where Microsoft develop deploy these thousands of machines with the FPGAs in their data center. So this is published in a series of papers, including ISCA 14, IEEE Micro. And then they show that Microsoft is using FPGA. So this is the FPGA board they use. And this is the architecture that they put FPGA in the data center. And they use such kind of like a scale out and a big scale, large scale computing with FPGA accelerators for their different services, including Bing Search, Azure Machine Learning, And they also use this in their like NIC. This is a network integrated circuits. Smart NIC applications. So the key idea is that if we want to, let's say, send the data from one CPU server to another CPU server, and then we need the router, we need the network router, right? What if like we put this FPGA sitting bumping the wall while transferring the data from one server to another server? We can do some like application acceleration in this data routing. And that's where we can do the offloading for machine learning task, or let's say the compression, decompression task, and also like let's say a database certain like operation, so that we can do such kind of thing in using FPGA and shrink this latency, reduce the latency by a lot, and then to increase the quality of services within those data center scale services. But the thing is that can we design such kind of like customized domain accelerator within let's say a day, within an hour? So, well, I think the answer is yes. For serious programmer, like programmers who have experience programming C or C++, we can create circuits from the C or C++, and then program and deploy those circuits on FPGA by using high-level synthesis. So high-level synthesis is a tool, it's a compiler which convert these accelerator code, which is written in C or C++, and then generated circuits automatically for us. So here I show one example code, which is a stencil. This is a Blur kernel. It's one of the stencil kernel used in image and the video processing. And we just write this nested for loops, right? So here we have less than 10 lines of code, and then we generate the circuits which corresponding to the lower part of this. This is the circuits that generate. And this is exactly the implementation of the layout when we implement such kind of design on board, on FPGA board. So this highlighted, like the blue highlighted area, or those circuits that we use, and then those highlighted different colors or some other like processing elements that I highlighted in the circuit. So this is give you some sense that, okay, we can design this domain-specific accelerators. We can do such kind of DSA design in a short development time or short turnaround time. But in that case, we should see a wide adoption of FPGA in the field, right? Especially in the AI field. But check those publication date. So here, I think I listed some of the publication date. So what happened after 2020? So they published 14, 15, 16, 18, 20. Where's that FPGA being used in the data center after 2020? Where's that? So you might be curious, and I'm also curious, but I can guess some on by comparing those FPGA versus GPU versus CPU in the deep learning inference. So this is the performance study we have been we conducted in the year 2021. Here we show that for the vision transformer, and this is a integer 8, so that's a quantized machine learning model or deep learning model. And then this is a low batch application. So we give the input image as a 6, so that we compare this energy efficiency comparison for FPGA, GPU, and also the latest like server level CPU. So here we show the comparison result. We only show this FPGA versus GPU. So we have shown that for different applications, including DITT and all the way to LVIT. So these are different model variants for vision transformer model. So vision transformer model is one of the popular models there for image classification task. And here we show different bars, right? So different bars is corresponding to GPU T4. This is a 12 nanometer technology GPU. And then FPGA U250, this is a 16 nanometer FPGA board. And also show the latest GPU A10G. So this is a 8 nanometer technology GPU. So surprisingly, this FPGA board is the lowest energy efficient computing devices when doing this deep learning inference. So this is against our intuition. We have been claiming that FPG is super good and has a very good or achieves 10 to 100x energy efficiency over general purpose computing CPU, whereas GPU nowadays also achieves that kind of scale, right? So that's well, it says something. What happened? Why FPG becomes the most inefficient platform in deep learning inferences? So this is probably the reason why is that. So this one is the GPU platform performance on top applications over the years. So this one exited the years from 2016 to 2017 all the way to 2022 when this pictures is taken. And then we have shown different dots within this trend line, and different dots or the different generations of GPU. So it includes all the way from this Pascal GPU P100 to 2017, the Volta GPU V100, and then A100 Ampere, and then Hopper. So H100 is the Hopper architecture. So you can see that this performance or this platform performance in these different generations of GPU increase faster than the Moore's law, right? So the Moore's law is the transistor scaling over the years. However, NVIDIA has put forward their products in a way that it has a higher speed up or the faster trend line than the Moore's law. So why is that? So the reason from this jump, this significant performance scaling from the point A to point B is that starting in 2017, the Volta architecture or the Volta GPU introduces the Tensor Core. So this Tensor Core, you kind of think it as a specialized hardware unit within this GPU. And then those Tensor Core units are for machine learning applications or tensor operations. So they can do very fast matrix multiplication or matrix type operations in a very efficient way. So previously, you can think of it in a way that previously, if using GPU vector processing unit, or they call the SIMD, this streaming multiprocessor SM cores, it might take. I'll just give some examples. It might take, let's say, 16 cycles to finish a matrix matrix size 16 by 16 by 16. But now when using tensor cores, you can finish such kind of computation within, let's say, one cycle. So this clock cycle, it can finish such dense matrix operations. And over the years, when they put forward new generations of GPU, they keep upgrading or they keep updating those microarchitecture, that is a tensor core architecture, so that it can have higher computation throughput instead of computing, let's say, 128 multiplication and accumulation operations in single cycle. They can compute, let's say, 256, 512. So increase the density over there. And also they support more data types, including the integer 8, integer 4, those newer data types, or BF16 or TF32, those new data types for the floating point operations. So that's exactly the reason why GPU has introduced can introduce such a faster trend line in doing this machine learning or deep learning applications over the years, faster than Moore's law. That's behind the scene reason is that they have this specialized hardware and they integrate them and then upgrade them. So one question that pops out is that what if nowadays we have FPG plus tensor core, such kind of architecture, so that can we do better, and can we do such kind of thing that give us this benefit that we can accelerate the deep learning applications as well? So that's exactly the reason why we re-examine this performance and energy efficiency comparison among all those different computing devices. And now by using such kind of thing, which we call XFPGA, which integrates the FPGA plus tensor core, and now we have much higher energy efficiency, which give us almost 10x. So the fourth bar here is this XFPGA. Well, we have this tensor core on the FPGA fabric, and then we achieve more than 10x energy efficiency gain than the 8 nanometer GPU. So this one XFPGA is fabricated in 7 nanometer FPGA. So that's give us like a fair comparison because that's the same technology as the 8 nanometer GPU. So how can we achieve that? How can we do such kind of like energy efficiency gain, more around like 10x energy efficiency gain while using the same technology node? And not to mention we're the behind the scene is that we use the Tesla core, right? So if like we have the same Tesla core or similar Tesla core architecture, how we can have better energy efficiency gain? So why is that? So this XFVGA, before I explain all those details, let me give a brief overview and introduction on this XFVGA. So this is a commercial product put forward by AMD. They give it the name called Versa ACAP architecture. So this ACAP architecture, you can kind of think of that as a heterogeneous SoC, and it has this FPGA and also AI Tensor Core and also the processor. This is a general purpose computing. This is a CPU within the same system on chip. And this is the AI engine array, or that's very similar to Tensor Core. You can do this tensor operations on AI engine. And here's a programmable logic array, which is a traditional FPGA fabric. And then we have this on-chip interconnect NOC network on chip so that we can forward the data back and forth within this AI engine and also FPGA and also the CPU. So that's an overall architecture. And so I'm going to discuss these two works which we published on FPG23 and also FPG24 to explain that how we achieve such kind of like energy efficiency gain over the latest GPU platform, data center GPU platform, and by computing diverse accelerator from matrix multiplication. And then after this, I will discuss how we do further optimization and to achieve the extreme low latency accelerator, machine learning accelerator. So when we first study the application mapping on this Versa ACAP architecture, we have an ambitious goal, right? We have an ambitious goal so that we want to do such kind of, let's say, different or broad machine learning, AI, deep learning applications mapping on this ACAP. So we have several like application domain candidates, including the image recognition, natural language processing, the recommendation system, and also the medical image segmentation nowadays. So they also use deep learning models for image or health medical application. But thing is that in the first the story is like this. So after we have been working on this for a few weeks, the performance, or let's say the achieved throughput we can have on this board is only 49.5 GFLOPS. So to give you some sense, what does this mean? So this ACAP architecture, the theoretical peak performance is 6,400. That's 6,400. That's GFLOPS. So literally speaking, we, after a few weeks, and we only achieve less than 1% of this theoretical peak performance. So we after this we study like what's the performance bottleneck? Why did we only achieve less than 1% of the peak performance? And then we figure out a way to resolve this, and then we do this. We call the composing diverse accelerator, composing heterogeneous accelerator while using ACAP, and then we successfully boost the achieved performance on this platform when mapping the vision transformer. So this is one of the applications to 1600. So we achieved, let's say, 32x performance boost after using our novel mapping solution. So we give this novel mapping solution a name called Charm. And we generalize this smart mapping or like novel mapping strategy to other applications so that we apply this to the other application domains. And then we significantly improve the achieved performance on using ACAP. But how we achieve that? So in the first place, we give a thorough like performance analysis, and the reason in the first place why we cannot get a very good performance or out of the box good performance is because of these challenges. So first of all is that we have a huge on-chip processing elements, or let's say this specialized hardware Tesla core nowadays, right? So the achieved or the computation is super high. However, the platform or this board particularly have a very limited DDR or off-chip bandwidth. So to give you a comparison, so here we show the U250, which is a last generation FPGA board versus the VCK190, which is this ACAP board. So we have around 4.3x boost on the peak integer 8 performance, or FP32. This is a computation throughput. However, we have only, let's say, 30% of this off-chip bandwidth. So I believe some of you have used or applied the roofline model in your own accelerator designs, right? So in the roofline model, it says that we have a roofline, which is a computation roofline. We have another roofline, which is a communication roofline. And the slope of this scaling line is the data reuse rate, or let's say the signifies how many data reuse we should achieve to transition our design from the communication bound to the computation bound, right? So if we have a platform which has a very high computation roofline, well as a slowly increase like a communication roofline, then it means that we need a really good, a very significant, very large data reuse to maximize the computation on this board. So that's the behind the scene reason. So when we do this kind of mapping on using ACAP architecture, we adopt the same methodology so that we want to excuse me, we want to maximize the data reuse. We want to put our design in this computation bound instead of the communication bound, which means that we need to design this accelerator in a way that it has a huge data reuse. So which translates that we need a tiling or tiled or block matrix modification if we do this for matrix modification kernels, which is one of the most time-consuming kernels in all those deep learning applications. It means that we have to design our accelerator so that it has a huge on-chip buffer, and it performs like data reuse on chip. So that's exactly the reason how we do that. So we have this, for example, we have a huge matrix multiplication that we're going to accelerate. So in the first place, we allocate a buffer on those programmable gate array, that's the FPGA, the on-chip buffer on this FPGA. And then we have this smaller chip on-chip array on those AI engines. So we have to split those buffers on FPGA and then send the little tiles on those AI engine array so that we can still keep these data reuse while we let the computation part, which is AI array, to do all those tensor operations. Excuse me. And after the AI engine has computed all the result, and then we collect those results from those AI engine array, and then collect those results to the on-chip buffer on FPGA, and then send the result matrix back to the DDR, right? So that's the lifetime of this, let's say, a tiled or block matrix modification computation. So this is good. If we have a huge matrix modification, I think the performance is pretty good. We can achieve very good on-chip performance. Sorry, we can achieve a very good onboard performance, onboard acceleration performance. But what if this nowadays the matrix size is very small? So instead of 4,000 multiplied by 4,000 by multiplied by 4,000, what if now the matrix size is only 16 by 16 by 16, right? So that's the exact reason. If we reuse this monolithic accelerator so that we just map those accelerator on the existing design accelerator. So the way we usually apply this, let's say, one accelerator for different shapes of a matrix multiply is that by padding. So we pad this accelerator, we pad this shape in the DRAM, or when we transfer the data from the DRAM to on-chip, we pad the data and that we basically reuse this larger matrix multiplication. But the thing is that now the valid data or the valid computation and also the valid data we need for the computation is very small. It's only a very small amount of this total data we read from the DTR and the total data we compute. So that's exactly the reason why we have such a small achieved performance when mapping the small matrix multiplication on using the ACAP. Because we basically we wasted the energy, we wasted the computation. So the good side is the best side is that we can leverage all those like arrays of AI engine. One detail about this AI engine is that this is like a 2D array of such kind of AI engine. So each core is, you can kind of think of Tesla core if we have arrays. So in this way, this is like 8 multiplied by 15 in total, 400 such kind of AI engine. Then we want to do such kind of thing in a parallel way. And we just discussed that if we're doing this for small matrix multiplication, then without like a good mapping strategy, it could be the case that we waste a lot of energy in transferring the data and also in computing the data. So that's exactly the reason if under this smaller scale matrix multiplication, then the throughput or achieved throughput is very limited. We can only have this high throughput if we mapped such kind of accelerator or map the large matrix multiplication on such kind of accelerator. So this is the drawback of using one monolithic accelerator. So that's kind of like a shape mismatch is a reason that without like a clever mapping, we waste on both computation and the communication. So how we can solve this? So the key idea is that we can compose a diverse shaped accelerators on using this ACAP resources. So the key idea is that if we have this matrix with both large and small sizes, what if like we design diverse shape of accelerator, can design this accelerator 0, which consumes most of this computation resource and some bandwidth, off-chip bandwidth, but we can put this large matrix multiplications to accelerate on those accelerator. And then we can allocate a small piece of this hardware resources and reserve that for the second accelerator. And then we map all those small matrix size to this smaller accelerator. And here we partition these hardware resources, including those on-chip BRAM, including those computation logic, including those AI engine cores, and also most importantly, including the off-chip bandwidth. So we need to partition the off-chip bandwidth in a very good way so that those computation and communication needs in these two accelerators can both be met, and they can accelerate those different shapes of matrix multiplication kernels within the whole application. So that's exactly the reason. And then we want to do such kind of way so that it can be, all those design efforts can be abstracted away. So that's exactly how we do that. We first manually write those half-synthesis design and also this intrinsic C code, but then we abstract them away, put them as if you write your application, just give me your application description, and then we can generate those accelerator automatically for you. And you do not need to write those like hundreds lines of half-synthesis C code. You do not need to write those intrinsic code that runs on the AI engine. We generate those code automatically for you. So that's exact. We propose a charm, and then we actually open source charm on GitHub, so that if you're interested, you can just type search Google charm, and then you can find this GitHub repo. And now I think it has over, let's say, 110 stars, and the charm provides this novel mapping solutions that is composing this heterogeneous accelerator for matrix multiplication on versus ACAP architecture. And then we explore like different mapping solutions, including we explore like how many number of different accelerator we should put on this chip, and then how we should map different matrix multiplication kernels on using the different accelerators. And then we provide automation tools so that users can easily use our tool for their own applications. So that's the white box open source framework. And the charm give us such kind of like flexibility so that user and also usability so that user can just give those the AI models and also the hardware constraint as input, and then charm will generate those design files so you can see the generated design code, and also you can launch this backend census tool to generate those design. So those are the bitstream that are ready to be deployed on board right away. And then Charm, these are the details about Charm framework, but we have those accelerator composer, which explores how many number of accelerator we should design, and what's the resource allocation, how many DSP LUT we should allocate for each accelerator in using this Charm composer and also Charm DSE framework, design space exploration. And then we have this backend automatic code generator to generate those accelerator design described in Half Synthesis and AIE. These are the intrinsic C code that sort of program those AI tensor cores, and also they host the CPU C code that programs the ARM processor. And we have also some mathematical modeling on the line to guide these modeling and optimization when doing this design space exploration. So the key idea is this performance and modeling optimization, right? So we have this underlying a script and to help us to find those optimized accelerator design. But the foundation is the performance and the resource modeling for a single accelerator. So we first have this performance and resource modeling for single accelerator design, which we can literally take those AI model and resource constraint as input, and then we can find different different accelerators under certain resource constraint, right? But these different accelerators have different throughput. So these are we call the design a single accelerator design space exploration. And among all those designs, we can find, let's say in this case, at this point, which consumes the most hardware resource, but also gives us the highest throughput, right? So these are the accelerator candidates. And then we can use or leverage those single core DSE design space exploration for this diverse accelerator composing. So the thing is that we want to allocate those matrix multiplication kernels within this whole end-to-end pipeline, but then we want to assign those different layers to different number of accelerators, right? So we abstract this as a mathematical question, that is how to assign m layers in one AI models to n accelerators. And so this is if this is to doing this exhaustive search, or let's say this is it could be exponentially increase design space, right? So we are literally saying that for m layers we have a different choice, and for this is the n to the m scale. So this is not affordable. This is not scalable search. So that's why we refine the search algorithm, and we improve the search algorithm so that based on this observation that, okay, large matrix, so we tend to put them in the large accelerator, while small matrix, so we put them in the small accelerator. Why don't we sort all those matrix multiplication based on their kernel size, based on their computation size? And then we have we can do such kind of thing that, okay, for the sorted matrix multiplication, let's group them. And then for each group, we can assign one accelerator. So let's say now we have this fixed number of accelerator to 2, then we can find a diverse accelerator composing. And then we do such kind of thing for 3 accelerator, 4 accelerator, and iterate this. And take this two accelerator as an example. We want to find a grouping methodology or grouping way so that this now give us a best throughput for accelerating those 5 different layers, right? Or accelerating those 2 groups of matrix multiplications. So we can search this in a way that, okay, now we have this 4 largest matrix size, and then the 1 smallest matrix size, and then give me an accelerator system design so that one accelerator accelerates for another accelerator accelerate this one, and then what's the overall throughput. So we apply this single accelerator DSE for these 2 groups of sizes of matrix, and then generate one accelerator system, which has an overall throughput of 1.8, let's say teraflops. And then we change the grouping. We can do that for, instead of 4.1, we do this for 3.2, and then we search this again. And then we search all of this design space, and we find an accelerator system with 2 accelerator within the whole system, and then achieves, let's say, 2.0 teraflops. And then we do this iteratively and find the one that give us the best throughput. So that's the the story behind the scene, how we find by using 2-step search algorithm to find and optimize the accelerator system for a large number of different matrix size kernels or matrix layers within the deep learning. So we apply this methodology to different applications, including BERT large, this is natural language processing, and also this recommendation kernel, this is called neural collaborative filtering, and also vision transformer and multi-layer perception. So this is a visualization. So what are those disks? These are different circles. Actually, these are the disk size, or the diameter of this disk is the characterization of their matrix size. So the bigger disk they are, then the bigger matrix. So here in BERT we have in each so BERT has a multiple layer duplication of layers, and within each duplicated layers there are 6 large matrix multiplication and 96 smaller. So these are a pile of smaller matrix multiplications. And for vision transformer, they have also some large matrix and many more small matrix multiplications. So there are 768 smaller matrix multiplication. For NCF, this is for recommendation, and MLP, I'll say in MLP, these are dominated by large matrix multiplication. So for this different size variance models, which one do you think can give us the highest boost before and after versus after applying charm? So I guess you have some answer. It should be the VIT, right? Because VIT, vision transformer, has the largest size variance, and that's exactly what we observe. So here we show this performance, the super comparison among different charm strategy. So you can kind of think the first one is a baseline, where we do not have a charm. That's one monolithic design, whereas the last bar is the highest or the best performance we find after adopting charm strategy or specialization. And we do such kind of comparison for 4 different applications we just mentioned. And by using charm, we boost the performance for as high as 5x for BERT application and 32x for vision transformer. So this is one that achieves or benefit the most by using this novel mapping strategy that is composing diverse accelerator, given that VIT has the largest size variance within this application. And for NCF and MLP, actually we anticipate such kind of trend because NCF is dominated by large matrix, and MLP is mainly, they are all large matrix multiplications. So that when using one monolithic accelerator, if we carefully design this accelerator, then we can achieve a very good performance in the first place. But for those transformer application or models, we need such kind of a novel mapping solutions so that we find the best partition and also mapping strategy when doing those end-to-end application acceleration. So that's the reason we achieve such kind of like 32x. I think in the first few slides we show that we boost the performance from like 50 G-flops to 1.6 T-flops. And you might ask, can we do better? Actually, this 1.6 teraflops, 1,600 G-flops performance is not the end. If we have, let's say, this is by using the same chip, but if we have more off-chip bandwidth, then we can also boost this achieved performance to more. And we have a follow-up work which shows that if we have this more bandwidth and more off-chip, let's say DDR banks, then we can achieve more than 50 or like 60 or 70% of this theoretical peak performance. So we can certainly adopt a charm framework or composing this heterogeneous accelerator in different platform when they have different computation and communication configurations. And actually, after we find this, we think, okay, what if like we apply this to GPU? Given that the GPU also have those abundant computation resources, right? And also, can we do clever, can we do this like a novel mapping solutions on GPU? And before we step into this field, we actually give a performance analysis and performance estimation by using this composing heterogeneous methodology. So we estimated that even for NVIDIA, let's say even for GPU, we potentially can have some like throughput or performance gains. Given that also it could be the case that on using GPU for deep learning applications, it could be the case that some kernels they are in this computation roofline. Some kernels they are actually in this communication roofline. So if we can do a novel mapping solution so that it can partition this computation resource and the communication resource, and also the most important thing is that if we can allow those accelerators different streaming multiprocessors that run at the same time, but for different application kernels, which is not GPU programming model nowadays provide. So nowadays GPU programming model is that, okay, when launching one kernel, I use all this computation resource, I use all the streaming multiprocessor, and then after finishing one kernel, I launch another one, right? But if we have certain ways to do such kind of thing that we allow two different function kernels using partial resources of the whole chip, GPU chip, then we can potentially also increase the performance of the GPU as well. So we are studying this. This is an ongoing research. I think this is there are some prior works starting to discuss this, but we haven't seen like an automated framework on top of GPU to do such kind of like a code generation and then performance optimization. So this is composing heterogeneous accelerator, and I think I have covered the most important key idea or key takeaway for this composing heterogeneous accelerator, and then I have to skip the second one, but I want to show some results and the latest findings for those what we have discussed on using ACAP architecture. So the first one, the charm is optimized for throughput, right? But in the real application scenarios, it could be the case that different applications they have different latency constraints. So one example is that. So here, this is an deep learning kernel description for this vision transformer, and by the way, we have open source charm, and then within the open source repo, we also have this non-matrix multiplication kernels. So these are the kernels which are key or important kernels within deep learning. Without those, we cannot do end-to-end application. So we also have accelerator for non-matrix multiplication, including transpose. So those are the data reorganization and layer normalization, and also GNU. So these kernels as well. So we also accelerate those part of application, acceleration application kernel as well. And speaking of those latency constraints, So Zoom, let's say Zoom, the application, AI application in the Zoom and AI application in autonomous driving certainly have different latency constraint, right? So for autonomous driving, the latency constraint is shorter, much shorter than the video conferencing. And we have to honor those different latency constraints. If we have such kind of design that's super optimized, for example, used in the data center, we cannot migrate those design for latency constraint design, because it could be the case that those design though have a very great throughput, but miss a deadline or has a very long latency. So that's something we want to further explore. So we want to design our accelerator in a way that it meets the latency constraint, it meets the latency deadline, while achieving the best throughput or the highest throughput under this latency constraint, right? So this is a follow-up work where we study how we can design an accelerator system. Well, we call them sequential and spatial hybrid accelerators. So the key idea is that we'll skip the detail. I will skip all those detail, but the key takeaway is that there are two design strategies when designing these accelerators. So one thing is called sequential, that is very similar to GPU. We use all the resources, then we launch them in sequential way. So we launch one and then we launch another one. But this is a good for what? This is good for latency, but not good for the throughput, as it could be the case that we have the shape mismatch, right? So here are some animation to show this mismatch. I think we discussed that for char. And the second thing is that we designed this spatial accelerator so that we can do this multiple accelerator, and then we map them, and then we spatially call them at the same time. They can be launched at the same time. So that's good for throughput. The throughput is good. Sorry. Yes, it's good for throughput. However, the latency is long because now we have to afford this the initial latency when launching or pipeline feeding those pipeline spatial accelerator. So can we do a better way to achieve the best of the both worlds that achieves a good latency, a short latency, but also high throughput? So this is exactly why we propose sequential spatial, which combines the hybrid mode of these two strategies. And then we can design new accelerator systems that achieves a smaller latency. So in this figure, the left upper part are those designed or those desired design choices we want, because this part lower upper left part are the low latency and also high throughput. So by using our proposed new sequential spatial architecture, then we can achieve a design point which achieves higher throughput while lowering the latency. For example, if we have a latency deadline at 0.4 milliseconds, so the x-axis is the latency constraint. If the latency constraint is 0.4, previously the best design we can have are either A or either this design. But the throughput there is not good. It's like 5 or 10. By using SSR, this sequential spatial reconfigurable architecture, now we can achieve the design point as E, which give us meet the deadline, but also very high throughput, 18 teraops. So this is higher than previous design points. So that's a key point. And also in a very similar way, I'll skip the details here, but in a very similar way, we put this also as an open source white box framework. So this is if you click this GitHub repo, we can find our design framework over there. So we do this in a way that we compose the diverse accelerator, but the thing is that now we adopted this on-chip forwarding so that we can forward the data between those FPGA accelerators which implements those non-matrix multiplication kernels, and also those matrix multiplication kernels which are deployed on AI engines, and then those on-chip data forwarding. So in this case, we can forward the data on chip, and then we perform this fine-grained pipeline so that all those accelerators can start right away when the data is ready. So that's a key idea. And that's the exact reason how we achieve those low latency or constraint. We can achieve this high throughput under the latency constraint. And we show those. So these are trend lines for different design strategy, and ours, which shows here in the green one, have the better throughput under the same latency constraint. And this is a trend line which we adopt for the GPU. So here, this is a GPU trend line. This is our trend line. So this part clearly shows that, okay, the GPU cannot meet the deadline for this like extreme low latency requirement. However, our solution can give a very decent like accelerator design while under this 0.5, let's say, latency constraint. So that's the exact the key design key design like goals we want to achieve. So I think there are many like interesting like research questions worth to be discussed, and I will just give a few. So one is that can we apply SSR to the GPUs? And we discussed some, let's say, on-chip forwarding technology. We discussed some, let's say, multiple spatial accelerators. And the short answer is no, not for now, as the GPU probably hasn't gave us those like flexibility or user control, such flexibility to help the designers or help to allow users to design such dedicated accelerator. But thing is that if GPU cannot do that, what if like for next generation FPGA, can we design a better FPGA architecture to support both like flexible mapping and also this great performance? Can we achieve a balance about the performance and adaptability? Or what's the architecture insight for next generation GPU, right? So these are all the questions that we want to solve in the future. And excitingly, nowadays we are actually collaborating with the Core Lab. These are research groups from University of Delaware and Wayne State University to apply our accelerators for autonomous driving, these real-world applications. So you are more than welcome to check out the GitHub repos I just mentioned, Charm and also SSR, and feel free to contact me if you have any questions and also interest. Well, given that, I think that's all for today's discussion. Thank you.
Okay, I'm mute. Okay, thank you, Pepe. Thank you very much. It's very good timing. Okay, yeah. So I have several questions, but I first to give the opportunities for our audience. So any questions from the audience? And you can either unmute yourself or input a question in the chat box. Maybe I think maybe I can start first. So, I think both of two works are quite interesting, and so if my understanding was correct, so actually explore the opportunities that actually we allocated the multiple diverse accelerators and to give kind of the heterogeneous support because due to the heterogeneous characteristic of the workload, right? So my question is that, so yes, in your slides you mentioned about like the some workload like the BERT, the vision transformer, and so on. And we know that like for the currently emerging transformers, actually their architecture has already been, it's a trend that can be very kind of uniform and many layers that's kind of the same, and maybe there's not kind very huge kind of the variance that on the different layer sizes. And I was wondering, so for that case, that so how do you kind to adapt your approach to this kind of new scenario?
Yeah. So maybe we can discuss this in very short answer. So yeah, depending on the application characteristics, yeah, if the application itself does not have that huge size variance, then we can just use one accelerator, right? But if like this is a like a end-to-end application, it could be the case, end-to-end application, they always have such kind of like a variance for this kernel one or vision transformer in the pre-processing or the later stage is another application that they are now in a pipeline way, right? Then we have to kind of like finally we'll encounter some like model variance or like the domain cross-domain like acceleration. So that's where I think composing diverse accelerator will help in those general cases. Yeah.
Yeah, and I have another question that so how about the communications between the different accelerators?
Oh, that's a great question. So there are two ways. One is from this off-chip DDR or off-chip HBM bandwidth, but off-chip high HBM, high bandwidth memory. Or let's say if in certain cases we can do those on-chip forwarding. So within this on-chip buffer, we can forward the data from one accelerator to another accelerator. So these are two different design choices depending on the application. Yeah.
So because I think your idea is, so for myself maybe it was incorrect. So it's kind of a very interesting point that it has seems that it has some hidden connection to the chiplet. So it seems
Oh,
that
yeah.
so it seems that you have this kind of FPGA style chiplet, but within the FPGA.
Yeah, exactly. So I feel like we're discussing some future architecture or future FPGA architecture. Certainly, I think that this is a so this particularly is an SoC, not a chiplet yet. But I could kind of think that in the future we could see some like a architecture like this, like a heterogeneous chiplet where we have FPGA chiplet, we have a Tensor Core chiplet, we have, let's say, HBM chiplet. So that's one of the future like I think directions. And I'm now actually studying this kind of like a heterogeneous in package architecture. Yeah.
Yeah. So it's echoing. So I think your last few slides as so you're exploring discussing some kind of possible new future of the FPGA microarchitecture and the
Yeah.
fabric.
Yeah.
So because I'm not from the Xilinx, so whatever. So do you think that right now this is the current FPGA, the fabrics, it is kind of provides a good support to what you want, especially
So
for your approach?
from the AMD or like those commercial products certainly they have different consideration, but as academia we are exploring this such kind of heterogeneous FPGA chiplets. Actually, I just started an SF project last year. We have the name called refresh chiplet. So in this refresh chiplet, we want to integrate the different generations of FPGA together within the same like system package. So we want to actually fab those chips in using interposer based integration. So we'll explore the architecture and also explore different mapping strategy and also design automation tool and also mapping solutions on those systems. Yeah.
That's still used the existing FPGA, right?
That's to be explored. We can also fab some chips by ourselves and then integrate them together. Yeah.
Okay. Thank you very much. And
Thank
maybe we
you.
can discuss offline. Yeah. So
Yeah, sure.
yeah.
Yeah.
Yeah. So any other questions from the audience?
Excuse me, I have a question.
Yeah, go ahead.
So when you generate or when you're programming the PL side, the FPGA, are you sort of auto-generating like Verilog, or are you sort of generating netlist? What granularity are you targeting?
Yeah, so in this particular like framework we just discussed, SSR and also Charm, we generate the high-level synthesis C codes, and then we use the vendor like Xilinx tools like Vitis to generate the RTL from those C codes. So we generate C, and then we use vendor tools to generate RTL, and then generate the netlist and generate the bitstream. So we started from those C code, C++, high-level synthesis C code, but then we use vendor tools to generate all these programmable bitstream. Yeah.
Okay, thanks.
Yeah.
Any other questions from the audience?
Yeah, you're more than welcome to send me an email. You can just Google search.
So before I let you leave, one more last question. So
Oh, sure, go ahead. Yeah.
So how do you think that apply your approach to some other kind of the more homogeneous architectures? So right now, I think your approach is kind of heterogeneity aware, but for some other homogeneous, like the CGI and so on.
CGRA is actually a very like worth to be discussed platform, because in CGRA we also have such kind of like a resource partition a strategy. So I feel like a CGRA is like 2D arrays, right? Then we should there should be some like new mapping solutions to cut them into different section and then do those collaboratively accelerating. Actually, my first paper published in FPGA or FCCM venue is about a CGRA, and I'm actually re-examining that like mapping solution in that paper. Yeah.
Okay, thank you so much. So if no more other questions, let's thank our speaker again. So thank you, Pepe. So give us this very insightful talk, and I think I need some time to digest that, and then we can discuss offline. And
Yeah.
also thank everyone to attend our this week's seminar talk, and our next talk. I think after I will be the next Thursday, and so thank you everyone, and also
you.
happy holiday. Thank you.
Happy holiday. Yeah, bye.
Thank you, Pepe. Bye.